Hello, my name is Dr. Simon Schmidt. I'm head of the Department of Hygrothermics at the Fraunhofer Institute for Building Physics, and I welcome you to the next video about the Lighthouse project in Chennai, where we will discuss about the durability optimization. First, let me come to the basics of durability. What does durability mean, and how can we evaluate the durability? Then later on we will look into the possibilities to really optimize the durability and how to increase the lifetime of the construction. With that, I would like to start with the first thing about the optimization of the durability, which is the durability itself. Let's look at the influence of the climate on the durability of the construction. When I say we will look at the influence of the climate, I think we have to go one step back and firstly look at the possibilities or the definition of the durability itself. So let's give me a short introduction into the durability itself. What is durability? Durability is stated as the resistance a material can give to an external influence. And the climate is one of these external influences, which is just one. But we will discuss and we will look at this specific influence that we have. So let's have a look at that. The external influence, the climate. As you know, the climate everywhere on Earth is different. So we have to look at the location where we are located with our construction site and have to look into that and see what kind of climate is to be in that area. For Chennai, I have put together these graphs and numbers so that we can see where we are and how the influence of the climate onto the construction is. First, we see that the mean temperature in Chennai over a whole year is quite high compared to other areas. So we are around about 28.4 degrees Celsius. Also, the relative humidity is quite high with 72.2%. The solar radiation mostly comes from directly the zenith and has also a quite high amount. So there's a high amount of solar radiation, but also a quite high amount of normal rain. On the right hand side you can see how the solar radiation on the left hand side, the colorful plot, and how the rain is coming in from which direction. So the main rain direction is southwest, which means especially to this direction we have to look deeper into. The second thing that we have to look at if we go for durability is the material itself, because we said the durability is the resistance of the material to the external influences, in our case to the climate. The material properties can be determined by lab testing. So we can do a lab test and look at the material that we are using and determine, for example, the vapor diffusion, the moisture storage, or the water uptake. These material properties are especially for moisture and moisture transport, and also water and water transport within the material, as we know that the water is quite a problematic thing in the durability aspects. Is there too much water inside a construction, there can be different possibilities of durability loss or also resistance loss. If there's too less water in it, same can happen. But let's have a look at the water and what the water can do within the construction if there's too much water on it. So the consequences, if we are not looking at that, is that we are going into, for example, mold growth on the inside surface or sometimes also on the outside surface. That we can see condensation on the inside, maybe on the windows, but also on the wall, on the inside, but also on the outside. And this can also happen within the construction. If that happens, there is a possibility to a degeneration of the material itself, which then leads to a lesser durability of the material. One of this example, one of the degradation of the material can be corrosion, as you can see it on the right hand picture. So corrosion is also introduced by water. So if we can manage the water in a way that this is less applicable to the material, then we also can manage corrosion in a certain area. So as we have now seen external influence, the climate, the material resistance, some material properties, and also the consequences if we do not look at it, or what can come out of it, the next step then would be to look into the durability evaluation methods. How can we go from the point that we know there is something happening to what is happening there? What can we do? What steps are to be taken? One of the steps that we are doing is we evaluate the materials and the systems. We can do that in different kinds. We can do that, for example, for fully fledged systems in some kind of field tests. I have provided you a picture of some field tests where you can see different wall types with different insulation, but also different materials, where we introduce these materials to a harsh outdoor weather condition and see what is happening over the years. We measure it and then we recalculate it. And then on the second step, we also do lab tests for the material itself. So in order to know the material properties, we can look into these materials by measuring them on the different scales in the laboratory. So we gain knowledge about the material and we gain knowledge about the systems in terms of their durability. This is one step, mostly the first step to gain knowledge more about the materials and the systems itself. The second step then would be to calculate what is happening, because durability is a long-term word. So it's not just for today, and will not look at things which is just from yesterday, but we look at things into the future and we have to pre-calculate what could happen. So what we can do is we can calculate the moisture content within a material, as you can see it on the left-hand side. We can do that by arithmetical evaluations of the durability. This is one method which is very vague and which is, but on the other hand, very fast. And then we can do hygrothermal simulations of the durability. So we can model the system, we can model the material, and we calculate what is happening in the future. What is happening with the moisture in material. And with that, we can gain knowledge about the moisture content within the material, and we then also can gain knowledge about the durability aspects if we know the model well. So this is the kind of evaluation of the durability through hygrothermal evaluation. The next step then would be to look into the durability optimization. So we do have some kind of material. In your case, I have looked into the concrete pre-construction, the precast concrete construction that you have, and we go into it and look what we can find out using the hygrothermal durability simulation in that and how to optimize that. First, I would like to show you the first step. So on the left-hand side, on the bottom, you can see a rough graph of the material. So we have on the left-hand side a plaster, we have the concrete block itself, which is the precast concrete, the material you're using with the material properties I have shown you in another video. And then on the right-hand side, we also have a plaster on the inside, which could also be just a painting. And I have then introduced some optimization possibilities. We have talked about these possibilities, or we will talk about these possibilities in another video, where it's about the energy efficiency enhancement. So I have introduced the internal or an external insulation, which you can see on the middle, the internal insulation, and on the right, the external insulation. And what I've done now is I've pre-calculated that with the hygrothermal simulation in order to see how the moisture content within that material will be in the beginning and also in the end of the calculation, and I have calculated over 10 years. And what we see is that in these graphs that are implemented here, the red line always is the starting point. This is normally the basic moisture which is in the construction, which is normal, and it should dry out in some kind. So if the blue line, which indicates then the dried out calculation or the calculation after 10 years, this blue line, this should always be below the red line. If we look at these graphs, we can see that from the left to the right, it's always alike. So we are not on none of the points we are with the blue line above the red line. What we can also see is that by introducing the insulation on the inside or on the outside, in that insulation, the moisture content is quite low. But we can also see, if you have a look at all the niveau of that moisture content, it's more or less the same in all the constructions. So there's no change in internal condensation, in internal water content using an internal or an external insulation. So there's no enhancement, you can say, in terms of durability looking at that. But as I said before, one consequence could also be that we have on the inside, for example, some kind of mold growth. For mold growth, we're using these kind of graphs you can see here. These graphs indicate on the gray curved line the uppermost area in which mold is growing, and on the dotted black line below that, that is some kind of, if there is a good surrounding, mold can grow here. And what we see if we calculate out of that measurement that I've done before and out of the calculation I've done before, these graphs that you can see here, and each dot you can see from the light green to the dark green one is the course of the calculation. So if the light ones are at top and it goes down below that dotted line, everything is fine. And then you can see a circle which is black. This is the final state of that material. So if that final state is good, in the end everything is good, so we do not have to do anything in that area. What we can see is that with all the possibilities, no insulation, internal insulation and external insulation, the rings are quite near that two lines I've described before. If we compare these, and I've done that with this horizontal line, you can see that the best possible thing in terms of mold growth, in terms of enhancing the durability about mold growth, is the right-hand side, because here we are below the dotted line and we have no areas where we are above that dotted line. So we can say there's no change in that optimization process if we use insulation on the inside or the outside in terms of the moisture content itself, but there is a difference in terms of mold growth potential that we have on the inside surface. So from that we can say optimization could be to introduce an outside insulation in order to reduce the mold growth risk on the concrete itself. With that, I would like to summarize what we have learned today. So the one thing is that we have just minor concerns about the mold growth. So every of these circles I have shown you is around about the same. But also the same is about the condensation within the construction. So I've showed you all are in the same area and there is no problem. And also in terms of the corrosion risk, because if the temperature is quite high and the moisture content is quite low, there is also not too much corrosion risk. But what we have not looked at, but which is crucial, especially also in Chennai, about the monsoon time, the outside has to be quite tight in order to really have a good protection about the weather from the outside. And that is the next point. So because if we change something from, for example, we try to cool the interior, the system change, and therefore also the durability aspects change, and we have to go through the process again, recalculating using the material properties I've shown you, or we have at hand, and go through the process itself again in order to see what then is the best solution in the end, enhancing the durability. So it's not easy process. First step is, as I've shown you, calculate it, try to look at the condensation within the construction, try to look at the mold growth potential, and then see in the end how it works. And if you change the system, re-go all the steps. And with that, I would like to thank you for listening and say goodbye until the next video.